Hello, everyone. My name is Henry Jones, and I will be presenting the impacts information technology has on scientific research. Physics for course AIT 600 at Towson. Alright, so on today's agenda, we will be talking about Moore's Law, supercomputers, parallel processing, quantum computing, and at the end, we will do a conclusion. So, on the image to the left, you see two galaxies merging together. Alright, so each dot represents a star within the galaxy, and to perform these calculations, it takes enormous compute power to calculate the movement of these stars when the galaxies combine. This is just one example of scientific research that IT systems aid in. Alright, so the importance of scientific research. So, scientific research advances humanity. In every corner of our life, we see how scientific research is impacting us. It solves real world problems, from coming up with a vaccine for the COVID-19 virus, to forecasting weather, to increase food production through genetic engineering. We genetically engineer our food to increase production, well, some of our food at least, and we want to explore the universe. We want to know what's out there. We want to progress. So, yeah. Alright, so impacts of information technology on the scientific community. Alright, so IT systems are propelling research forward. We have developed, as the IT community, developed tailored systems built to meet the demands of the scientific community. The scientific community requires enormous compute power to perform their research. Um, we are starting to utilize emerging technologies like quantum computing to perform calculations. Um, so quantum computing seems or looks very promising as the technology progresses. We are taking advantage of it today to conduct research. Um, and we take advantage of special processes and frameworks of supercomputers. We take we take advantage of a process called parallel processing, and we have developed special frameworks for the unique architecture of supercomputers, or today's most powerful computers. All right, so Moore's law. So one of the co-founders of Intel, named Jordan Moore, stated that the number of transistors incorporated in a chip will approximately double every 24 months. So I have this cool graph. So as you see, from 1971 to 2021, the number of transistors steadily increased. So pay attention to the axis over here. So from 2020 to 2021, it increased by 20 billion, roughly 20 billion transistors. Do a linear view, you can see it's exponentially growing the number of transistors per microprocessor. Alright, so let's talk about supercomputers. So one of the world's, or if not the world's most powerful supercomputer is Frontier. It was stood up in 2020. It's able, or 2021, I gotta double check that. But it's able to process 1.1 extra flops of data. It's the first supercomputer that is able to reach that 1.1 extra flop mark. So a supercomputer can be defined as a computer that performs at or near the highest operational rate for computers. Supercomputers utilize thousands of processor units grouped into compute nodes. So let's click this link. So as you see, um, this is the capability of the fastest supercomputers. So right now we are in 2022, and it's at 1.10 billion um, extra flops, floating point operations per second. So the graph looks similar to the transistor graph, according to Moore's law. Transistors aren't the only factor that performance of a computer, but it's one of the main factors. And we can look at the linear graph too. It exponentially grows as time goes on. All right, go. Click this one too. We can just do a brief overview. This is Frontier being developed or being installed. This is a diagram of the architecture of Frontier. This is the compute nodes of Frontier. This is the aisle view of Frontier. And this is the timeline of supercomputers. So Frontier is today's fastest supercomputer. Alright, so supercomputers take advantage of a process called parallel processing. So parallel processing splits problems into pieces and work on many pieces at once. Um, so imagine this group right here is one problem. It breaks the problem into tiny sections, and then each compute node can process each section of the problem at once at the same time to more efficiently and quicker come to the conclusion it gets the answer to solve the problem. Um, Compared to serial processing, if there's a problem and one piece of the problem is solved at a time in order. This is vastly inefficient. Takes a lot of time to process this data. Alright, so distributed computing. Um, this is when a computer process power is spread across multiple locations. So data centers, Amazon Web Service, big service providers takes advantage of distributed computing. They have data centers across the world that process data. I'm going to look at one cool example. It's called IBM WCG. Um, so it's a grid of volunteers that contribute compute power to a research organization cause. I'm going to have a quick video that explains this. I'm going to play the first 30 to 40
They
seconds
do
of
the
it
incredible.
after
Help
this ad.
save lives.
What if you could help find potential treatments for cancer while responding to an email? Or help study bacteria while setting your weekly agenda? It's easier than you think. When you're using your computer, you're rarely using all of its available computing power. World Community Grid lets anyone donate their unused computing power to support scientists working in humanitarian research around the world. All you need is a computer or Android device and an internet connection. You sign up, select projects you want to support, and install the app. Then you just let it run in the background. Your device does research calculations when it's idle, so just by using it as you do every day, you can help scientists get results in months instead of decades. But you may be thinking, what about my battery?
Alright, so yeah, WCG is a very cool uh, cause to get involved into. So you can donate your own compute power to advance scientific research. They will send work to your computer processes it, and then sends the process data back to the servers, the WCG servers. Alright, so we're going to look at the module architecture of supercomputers. So if there's a popular clustering framework called MSA that was created by the DEEP project funded by the EU fund. So it's a module design that matches the needs of today's supercomputers. Um, so supercomputers use unique algorithms to operate, and this framework helps make these algorithms as effective and efficient as possible. So it builds information systems that can dynamically adapt to the needs of a wide range of applications and enable the integration of diverse hardware, including quantum computing. So it's a module architecture designed for advanced scientific research. This is one way we are tailoring information systems to meet the needs of the scientific community. Alright, so quantum computing. Quantum computing is a very exciting um, emerging technology. So instead of processing binary ones and zeros like modern computers do, quantum computers uses a superposition of qubits. Qubits can hold a value of 1 or 0 along with the superposition of all possible states between 1 and 0. This quantum computers are able to perform um, small calculation of vastly many more small calculations quickly. And once we get to a mature state of quantum computing, technology has high hopes of progressing our compute power exponentially. This is an article of how quantum computing is impacting today's research. Um, so, researchers have utilized quantum computing to create a simulation of a wormhole. This is just a cool article you guys can look through. Uh, So in conclusion, IT systems meet the need, or is our IT systems meeting the need to progress scientific research? Yes and no. Scientific research demands are always increasing, and scientists would love more capability, more compute power. Um, Information systems are attempting to meet this demand, and we are hoping on the emerging technologies like quantum computing to vastly improve or vastly achieve the goal, to meet the goal of scientific researchers, to enable us to perform many more calculations quickly. Um, we discussed how IT systems are tailored towards research with parallel processing and the unique frameworks. And we discussed the impacts of today's scientific discoveries and how IT systems aid in that, from simulating galaxy mergers to weather forecasting to creating vaccines for today's viruses and illnesses. And I'm going to end it with a cute video of my girlfriend's cat. His name is Socks. So I'm going to play it, and I hope you guys enjoyed. Thank you. He grabs a paper from the printer.
Go.
All right, thank you guys.